It's my pleasure. Welcome to what do we call it? Not an irregular EOL seminar. Uh, Not quite our normal time or space, but it'll work. And it's my pleasure to introduce Ian Giammanco.
Very good.
Okay. And Ian got his bachelor's in atmospheric science from University of Louisiana at Monroe. Got a master's also in atmospheric sciences, but this time moved to Texas Tech, where he stayed to get a PhD also. And I should have asked you who your advisor was.
That's John Schrader at Texas Tech.
Okay. And that was using WSR 88D observations of tropical cyclones along with GPS. So he still has an affiliation with Texas Tech as a faculty research associate. And among other things, while he was there, was involved with the development of StickNet, that we know as hopefully SentNet will grow from StickNet's experience, and is now with the Insurance Institute for Business and Home Safety, and among other things, has been doing all kinds of interesting tests on hail impacts, fire impacts, and other things with lab testing. So I'm sure you'll tell us a lot more. Welcome.
Thank you. Yeah, this is a little different flavor than probably what everybody's kind of used to. And instead of talking about my background working with GPS SON data and the 88D, I wanted to talk about some new work that I've been simply started down the road a couple of years ago at the Insurance Institute for Business and Home Safety. And just what that is a nonprofit research and advocacy group with the mission to simply mitigate natural hazard losses. That's the overarching goal of the company. So for the insurance industry, hail is nearly a $1 billion annual insured loss every single year. So they're very interested in looking at how can we find ways to try to mitigate against that loss. And so this was a project or kind of ongoing research area that took me out of my comfort zone as a boundary layer wind guy into the world of hail, which I didn't really think I would end up doing work in hail, but it's been an interesting road so far. So I wanted to kind of share a little bit about that. So this will blend a lot of more so kind of instrumentation design as well as a little bit of the engineering aspects of kind of how all these pieces fit together and how we examine hail. So kind of a bit of an overview. This is kind of a part one and part two. The first part I'll talk about is investigating the material properties of hail. And then I'll go on to something that's very new and very interesting to me is taking the StickNet adaptive network concept and just applying it very simply to hail. Can we deploy a network of observing platforms out ahead of a severe thunderstorm and have it collect hail observations? And got a first case from this for one of our prototype instruments 2 weeks ago. So this went and pieced together something real quick, and I just thought it would be nice to share with this. So as I mentioned, hail events are a huge source of insured loss. So the insurance industry, and I should preface this, that our company is funded by pretty much, it's a membership basis through any big property insurer you can think of. They pay a membership, and that covers the budget side. And so they dictate the areas of interest. And so hail, being a $1 billion insured loss issue, they are very interested in. And what also drives that is that risk or catastrophe models that are charged with estimating essentially an insurer's exposure or the level of risk they want to take on as a result of an individual peril really struggle with severe convective storms. This is a very new area for them because losses keep going up and up and up. So they're essentially kind of fighting from behind to catch up with their severe convective storm models, whereas hurricane risk models have been around for a long, long time. There's quite a bit of information already there. And then the next goal is can there be mitigation strategies? Are there products or testing scenarios out there that will help come up with certain strategies to reduce those losses? And then another kind of added piece is looking at cost benefit versus event frequency. How does a material perform against certain types of hail, hurt certain sizes of hail, versus the cost to replace it. And if this is all the things that drove the want to get into looking at hail. And so that's kind of where we'll start, is just kind of examining kind of what got us into this realm. So the first bullet, some of the questions that you ask, does damage purely scale with impact kinetic energy? And I'm going to use the pictures on the bottom, and let me, if I can, that's a little better look. So we can use the cursor here. There we go. This is a 4 centimeter ice ball impact on, these are all the same products. This is a new product. You can kind of see the edges where it cracked the shingle. Same product, 2 years old, multiple ice ball impacts, same type of ice ball impacts. You can see there's definitely a difference there. You have a whole bunch of that darker area. That's granules, those little grits of rock that come off of shingles. And what is actually known is when you knock off those granules, that asphalt material will undergrade or degrade with time due to UV exposure. So that degrades your shingle. Your roof will eventually not perform how it should. And then the very standardized test that everybody does to essentially rate a shingle, the product rating, is a steel ball impact. And you can obviously tell that the damage patterns just look different. They just visually look different. So in the steel ball impact, you have these little grits of granules just get crushed. You don't see that in the field. You don't see it with ice ball tests. So we wanted to explore, are there better standardized test methods that actually account for this? And some of the other things, does shape of stones matter in damage? We've all seen the very spiky, loby structures of hail. They're not perfect spheres. Obviously, a lot are disc shaped. Those are oblate spheroids. So does that matter? And these are all the questions that we just kind of started down the list, essentially wanting to look at. And then taking measurements from the field of hailstone characteristics and applying it to laboratory testing. So I'll kind of continue on. There's always been a qualitative description of hail, whether it's hard or soft or slushy. And I absolutely love the quote at the bottom from the Knight et al. Paper in 2008 from a very unique hail event here that mentioned a very unique, or what they deem unique type of hailstone that it ended up stripping trees of leaves and some twigs and branches, but there was no noticeable property damage. And so, why is that? What's causing that? Or are there hail events that will cause, there's some characteristic of them that will cause some kind of enhanced damage? So taking that, moving it over to the material science world, they often cite a lack of information on the material properties of natural hailstones. So the standardized tests are all just assuming that an ice ball impact is a worst case scenario. Now we know hailstones, the density is slightly less of that of pure ice. So where does that fit in? These are all some of the questions that we wanted to try to figure out and provide some information to get at. And I want to go back and actually show this high-speed video because it kind of shows an example. A couple of ice ball impacts on some shingle materials, and it's always fun to look at high-speed video too. But there's one in particular here at the end that's coming up, and it just gives you a flavor of what impacts looks like. The stones where they completely shatter on impact, but there you have an ice ball that's hard enough that it just bounces off the shingle. It was the damage mode different as a result of that stone that simply rebounds off the material. So those are just some of the kind of observations and questions that I kind of asked. So how do you tackle hard and soft hail? And throwing around just ideas with some of the engineers that I work with, we thought of an idea: how do you get at some of the material properties? So our first stab was based on really hard object testing, so concrete rocks. They simply crush them and look at the peak force required to crush them as a measure of their strength. So we're looking at material toughness. So it's the ability of a material to withstand and absorb energy without failing. So the ability to still support a load on it. So if you're pushing down on it, it can still support that load. And it's simply the integral of the stress-strain relationship. Well, we thought, okay, is there one of these quantities can we measure? And ice is something, and I'm going to define strain rate here, is essentially if you're trying to crush something, it's the rate of displacement of the piece that's pressing down on the specimen versus the diameter of that specimen. So ice, if you're slowly compressing it, it will be very ductile, meaning it will want to compress. Ice start to melt a little bit and compress and hold its shape. But as you increase that displacement rate and so forth, strain rate, you'll get a brittle failure. It'll essentially shatter, so cracks will start to propagate through it, and you'll get a very sharp peak if you look at the applied force versus time curve, and that's kind of this bottom conceptual graph that you'll get a peak. You can record that, and that's essentially the peak load that that object could support before it failed. So on impact, a stone impacting a surface, that strain rate is actually very fast. So ice induces a brittle failure, so we should have that peak. We should be able to measure that. So how can we take that to the field? How can we go out and actually collect hailstones and really measure it? And here's what kind of we started with. This is what the strain rate versus compressive strength looks like for ice. And you can kind of see at low strain rates, we're talking about that ductile compression where the thing just kind of compresses and holds its shape. You'll start to see an increase in the amount of load it can support. And then it kind of levels off in this kind of general range. So strain rate is in the units of per second. So that flat kind of leveling off area where you get that ductile to brittle transition occurs right in there. And so we want to get a brittle failure. So we have to come up with a device we can have in the field that can produce that. Now in a lab, you would use a universal test machine or something that can apply a known load, very cumbersome, clunky, very large object. Usually it can be referred to as instrons. That's a manufacturer. So these are kind of the standard test rigs, but it's hard to take one of these. Yeah. This ice is it is not at this point. These stones, well, I should preface, there is a dependence on temperature, but if you look at ice, say from minus 10 to minus 30 C, there will be a difference in the amount of load it can support. If you measure the surface temperature of the stones when they're tested, you're usually right just around there, but just below. So the idea is as stones, and I'll kind of get to the melting issue in a little bit. So you couldn't take one of these large apparatuses out to the field and actually go perform some of these tests. They're just too cumbersome. So we needed a device that would actually kind of get to this to brittle transition there and produce that brittle failure. And so that was the idea. And a theme I'm going to talk about throughout this talk is low cost. In the private sector, large scale research projects that are high dollar things are really, I say they're just kind of frowned upon. You need to try to make it cost effective and one to be able to get to the field. So you needed something that would produce a strain rate high enough to get that brittle failure. And you also have to resolve that peak. So you need fast sampling. And I put on there greater than 100 hertz. It really comes down to about 1 kilohertz or so. It's got to be transportable, easy to use in the field, and as I mentioned, cost effective. And so the device we actually kind of ended up with, and that's what some of the data looks like, is a simple handle device that you manually apply the load. There's a load cell down in the bottom apparatus that measures the amount of force that's being placed on that stone. And so you get a record that looks like this, where you have a very sharp peak and then the drop off. And that peak is what we're interested in. That's the peak at which it no longer could support the load and actually fractures. So this is just an example actually from a couple weeks ago of a stone we measured in the field. Now, I will say there are some drawbacks to this kind of simple system. Whereas a universal test apparatus, you can apply a constant strain rate. This is manual operation, so you don't get that very clean displacement rate. But we did some comparisons with a universal test machine and actually came out fairly reasonable. And I'll get to that in a second. So what we kind of chose to use was a 500-pound or 2.2 kilonewton load cell. It's in the Wheatstone bridge configuration, so it's an array of strain gauges. And then we use a signal amplifier board to produce a plus or minus 8 voltage output signal. The device itself is calibrated using a dead load, so we would actually put the device into an instron, essentially press down on it with a known load, and develop that voltage versus load calibration curve. For the field, we actually use a National Instruments USB data acquisition module using a LabVIEW interface. So we collect all the information about stones in LabVIEW and run the device essentially off of a LabVIEW interface. So in doing the Instron comparisons, we actually took the field device. We're sampling at 1 kilohertz. We're also sampling the Instron at 1 kilohertz, and try to hit we use the target strain rate for the Instron. So we're right in that 10 to the minus 1 seconds to the minus 1 range. And we did some photogrammetric work with the field device and using a displacement transducer just on one, but the cost of that kind of drives things up a bit, to look at where our users essentially, what strain rate are we actually producing with this field device. And there is some variability, but we landed in that 10 to the minus 1 magnitude. We didn't jump, nobody jumped up in order of magnitude. So we thought, okay, let's take a stab at this. And so you actually look at, these are all ice spheres. This is just the peak compressive force at the point of fraction. You can see there's quite a bit of variability, and this is simply due to the kind of the properties of ice itself. You'll get micro fractures just simply making ice spheres and molds. So you get some variability there. But if you bin it and group it into means there, we got a pretty reasonable performance. And some of the error there, once again, due to the manual operation of the device, but we were actually able to come very close. And there's some differences. You can see kind of the mean diameter in the bins kind of shifted a little bit. This just had to do with the style of molds and the performance of molds when you put them in the freezer, so you kind of have a little difference. But in general, in a mean sense, we did pretty well with the device compared to the Instron Universal Test Machine. So for that, I think on an average scale, we can use that information. We can look to see, is an ice ball comparable in a test sense to what a natural hailstone would be. We can get an idea of that and get a relative kind of measure of essentially kind of the general hardness characteristics of natural hail. So evaluating the compressive strength, we want to look at that uniaxial compressive stress, so the peak compressive force at fracture scale by the cross-sectional diameter. Another source of error that comes in when you're in the field, to compute that cross-sectional area, you make an assumption that they're oblate spheroids. So in the field, we measure the major, minor diameters, but as anyone who's ever looked at hail, there's a variety of shapes, and that's not necessarily valid. It's just very hard to get an accurate, a whole bunch of different dimensions of a hailstone in a timely manner. So that's a source of error that kind of creeps in here. The compressive stress, when you scale it by the cross-sectional diameter, you remove any trend, like I just showed with that increasing compressive force with size. So that essentially detrends that, and you get this relative measure of the strength of a stone. So the disadvantage of the device, it's not a true constant strain rate because you have a manual operation of it. Fracture versus the ability to support a compressive load, and I'll talk about this a little bit later too. In the lab, ice stones you'll have a piece break off along a pre-existing microfracture, but the stone itself still maintains the ability to support a load. In the field, natural hailstones, in a very qualitative sense from observing, testing about 1,000 stones, they'll just fracture in a very sharp peak and fracture into a bunch of different pieces and have no ability to support a load. So on an impact, you could see some differences creeping in there. And there's really not a great way to handle that. And these are some of the things you just have to deal with. And of course, in the field, the measurement of the shape of the stone comes into play. How is that oblate spheroid assumption? Is it good enough, or is the error too significant? So 2012, 2013, and actually ongoing into this year, decided to do a field project. And our group is a very small research group. So executing a field project is somewhat of an endeavor, and we actually drugged some of our office assistants out to the field and had them measuring hailstones or helping us even just drive vehicles. So the idea would be to quickly approach a hail-producing thunderstorm as safely as we could without essentially getting our cars obliterated, quickly collect stones in an insulated container, and then do a series of measurements. Usually what we would end up with is only about 20 or so stones we could collect quick enough before we had significant melting, and we just decided to not conduct the test. So it's very hard to get large numbers because it does take a little bit of time, and you're having to try to quickly collect them and then go through kind of your systematic measurement process. So in terms of if you were just going out and measuring hail diameter, you could probably do thousands of stones. But over 2 years, we're just now to that 900 mark, and I think we pushed it over 1,000 with a case this year. So we measure the major and minor diameters, we weigh each stone, and then perform the compressive strength test. We also photograph every single hailstone, so we actually know what kind of the layering structure looked like to see if. Yep.
Can you get some of that information from hail pads?
That's for the size distribution. Hail pads.
Also, maybe the depth gives you the mass.
Yep. It,
Dimensions.
and on that end, we're actually trying to look at an automated way to make some hail size distribution measurements, and we've actually taken some of the older hail pad data, and that's I'm going to get off topic just a little bit. That's of interest to the catastrophe model people who are assigning a damage state based on some assumption of hail size distributions, and that's something that they're have always been interested in, and I'm not sure they know where to go find that kind of information. But yeah, hail pads definitely get you all the size and depth, and I'll get to some of that here in kind of part two. So we take a photograph of every stone to actually just see what are does it have a layered structure? Is it just that very opaque ice with maybe clear ice surrounding it, and then perform the compressive strength test. So in this 2-year period, you have about 19 supercells in there, 4 linear convective mode cases, and then 2 general kind of unorganized, what I would consider unorganized cells. This was based on a radar classification scheme. So traveling from, our lab is in South Carolina, so we would essentially take a week, fly out to the area, and just go make our hail collection. So we essentially try to make a decent forecast that we'd have some severe weather. And this is a plot I kind of quickly threw together because I haven't had a chance to make a really good one compared to the historical work. I added in here a recent study by Swift in 2013 that was looking at pure ice compressive strength tests, and that's the blue dots. Everything else is based on ice cylinders and other evaluation of the compressive strength of ice grains, and that's what the curve looks like. You can kind of tell the Swift study had some variability, and I just plopped on there our field observations, and that's generally representative, plus or minus a standard deviation from the whole group. So it actually fits reasonably well with what you'd see, with the observed variability there, with regards to pure ice. So if you looked at the effect of melting, and we collect stones after they've fallen, there's so much variability in there, it's hard to even extract where that comes from. So you could pick up a stone that might have been on the ground for 15 minutes and it'd be extraordinarily hard, or you could come, you're right behind it, and the thing's only been there for 5 minutes or so, and it's just slush. It's hard to back that out. But overall, what it would tell you, if you're going to do a material test based on an ice ball, is probably a reasonable assumption to use that's representative of just an average state. So if you were looking at revising material test standards, that may be a quality way or a reasonable way to get away from that steel ball. So you can even go as far as, how do the physical stone properties matter, the growth processes, the dry and wet growth, which produces the layering structure, how does that play in? But those are just kind of general bullets that you could start to work on. Now, if you scale that compressive stress by the mean of the pure ice information there, and look at the distribution, you actually get a mean where natural hailstones are about 6%, at least a little bit stronger, but again, there's a lot of variability. Maybe the mean's not a best metric there, you use a median of distribution. But from individual events, you actually get a wide range of these values. So you go from very slushy, that simply compress only under maybe 16 pounds of force. And I'm going to flop units because I work with engineers all the time, and so we jump back between metric and English. But and then you'll get other stones that are extremely, extremely hard. And I actually saw this in the field a couple weeks ago. We essentially maxed out the strength device. We applied over 700 pounds, exceeded the range of the load cell, and the stone did not fracture. So that stone itself, I have no idea what about it made it so tough, but it did not produce a fracture, nor did it compress. Now, 5% of the stones we've actually collected in the field, even at our strain rate that would produce a brittle failure in pure ice, simply compressed and held their shape. Whether these are the spongy stones that the literature talks about, I'm unsure. But even at that strain rate, they simply compressed and held their shape with no noticeable fracture. And you can actually see that if you look at the raw trace of the compressive force information. And in general, the strongest stones, the hardest stones, were typically not the largest. So some of the smaller ones actually had some of the larger compressive force values. So kind of interesting to see that. And where does the spectrum of kind of hail fall? And we can throw on the storm types, the QLCS and supercells. And I did that only because QLCS, the only ones, we have 4 cases, were 30% weaker than pure ice. So, what about that environment is producing a very weak hailstone in a linear convective mode? And we barely have enough cases. It's probably even hesitant to even try to make that connection without more cases since our data set's dominated by supercells. But that was the one noticeable thing. And again, it's not necessarily the whole story because lab stones can fracture but maintain the ability to support a load. So maybe you're biasing that result. Maybe supercell, those hailstones are not necessarily as strong because lab spheres can still maintain the ability to support a load. I mentioned the natural hailstones fracture into a bunch of smaller different pieces and just cannot support a load typically. And then I mentioned that small percent of natural hail had that just kind of general compression. So for material testing, pure ice spheres, is it the worst case impact? Is that really true? I don't know, but is it reasonable to consider just kind of a mean state? Probably so. So that's probably a better way beyond the steel ball test to test a shingle material or something like that. The standard test from FM Global, which is a risk insurer, is an ice sphere, but it is not the product accepted. The one that everyone uses is this UL 2218, which is the steel. It's simply a steel ball drop. So it's simply kinetic energy onto a building material. And then an interesting one to drop the density of stones, the ASTM F320, this is an aviation test, uses cotton fiber fill to drop the density of their laboratory stones. And, the last question there is where does density fit in? And out in the field, when you're just measuring 2 dimensions, the non-homogeneous shapes of hailstones make doing a density calculation almost impossible. And if you want to do an immersion test, does that affect the compressive strength test? And is that practical to do in the field? Can you sit there and immerse the stone in a liquid, get your volume that way? Is it too cumbersome? And we haven't actually tried that, and I'd like to give it a stab. But a technology we've actually looked at is 3-dimensional laser scanning. This is a scan of 2 laboratory ice spheres using a laser scanner system that will produce very highly accurate volumetric measurements of essentially anything you want. So we were able to actually, it's a handheld laser scanner, and you just swipe it. Probably takes about 30 seconds to do a complete stone. And you get an image that looks like this. These notches, I took a screwdriver and just chipped notches to see if the scanner would resolve them, and it actually does. So we could imagine taking this out to the field and actually making very highly detailed, essentially 3-dimensional maps of what hailstones actually look like. Then you could print a mold, make a shape, or for the radar folks, you can look at cross sections that way. Some interesting different applications of that, and that was a neat kind of concept to take a look at. The second piece of this is something that's kind of near and dear to me, is adaptive and deployable observing networks. We took a stab at essentially an automated hail pad system, and it's based on a NASA design from 2006. And we really wanted to see, could we apply this idea in a simple fashion that's cost effective, kind of like I did at Texas Tech and the group with StickNet. So a bunch of probes you can deploy out ahead of whatever feature you want to measure, let it pass over, and you get nice time histories. You can do time to space conversions, et cetera, et cetera. But for us, got to be cost effective. Got to come up with a way to reduce the cost and to do this. And so the research goals were try to get at spatial and temporal characteristics of hail at the ground as a variety of applications. For our world in the insurance industry, it's to be able to refine how the severe convective storm catastrophe models handle the dimensions of their hail swaths. So that's what we were trying to get at. But there's all these other things. You can throw in polarimetric radar hail detection, numerical weather prediction parameterizations when you're producing a synthetic hail swath from a numerical weather prediction model. You could start to look at some of those things and use it for validation. So the idea was taken from the work quite a while ago, and just looking at piezoelectric disc and how they can handle impacts. So the output in general, the voltage signal will scale with impact energy. And so we took a concept that in the Lane et al. Paper of a fixed platform hail disdrometer that NASA used at Kennedy Space Center to try to see if we could turn it into a mobile application, and one, to see how well it could do. This same concept is applied on the Vizsla WXT all-in-one sensor, but the thing is just not very rugged. So if you get into big hail, you're going to essentially obliterate your instrument, and that's you're going to lose that in cost. The other ways to do it, particle imagery or photogrammetry, but once again, it's kind of you start bumping up costs. So in a system, if I was in StickNet, we said, all right, what kind of data acquisition system would we use? We went with NI, National Instruments component. So if you look at like a compact Rio data acquisition system, you're in that ballpark, 3 to 10K range or so. Or Campbell, DAC. We're not down at developing our own controllers. These are easily configurable, good hardware timing, so very high sampling rates. You can easily configure, especially the NI systems, if you're good with LabVIEW. They're rugged and they have good data storage capability, but they're costly. And for us, trying to sell a network of these at that kind of cost just wasn't going to happen. We have a fixed budget, and you would eat up a lot of it. So could you look at some of these low-cost developer microcontroller platforms without actually sacrificing your measurement quality? Can these controllers, we're not down to taking the individual processor chip and making our own board, but can you take some of these developer-type things, a combination of, say, the Raspberry Pi controller system, which is essentially a computer, a Linux machine, an Arduino, the Mosaic, the PDQ board, something like that, and adapt it to work in this type of platform. So we took a stab with one of them, and we had kind of this general design criteria that we needed to resolve hail roughly greater than a centimeter. We needed good sampling, so high resolution sampling, and then good mounting for the piezoelectric sensor that would essentially send out a voltage signal that would look like this on an impact. So you get the peak of impact and then a time duration of the actual impact duration. So that's kind of what it would look like. So we were going to take a stab at this acoustic sensing technique. And then the other side is they got to be rugged, so they got to be able to take big hail, and you need to be able to deploy it in less than 3 minutes. So that was 3 minutes is what we used for StickNet. So I was like, why not? We'll use something similar. It was very successful that way. So we went with the Arduino Uno, which is one of the base lower levels of Arduino controllers, and then added a GPS shield. It's made by Adafruit that incorporates a GPS module. You can actually see it right here. It's got a hardware timing. That's a battery to maintain the hardware clock. SD card data storage. So we do everything with micro SD card data. And we have this nice prototyping space to be able to add screw terminals and integrate the underlying Arduino as you fit it over the top of it. So kind of easy integration to get your GPS time syncs as well as your good position location on board the platform. And for the Arduino, we have 7 analog inputs and a handful of digital IOs. And I'll kind of get to the nitty-gritty of that. So the first couple tests, we were actually able to achieve a sampling rate of 700 hertz. One of the disadvantages of this type of system is the language it uses. You're kind of restricted on the amount of code you can actually apply. Any type of computation within the structure of the code that runs the processor will slow down your sampling rate. So you have to be very mindful of all these little things. And it's something I wasn't used to with kind of LabVIEW and MATLAB code and things like that, is to try to make sure the thing will run as fast as you can. And understanding, when can you fill up the memory buffer and then write that off to memory, so you're not eating up clock time writing every single line of data to memory. So it can handle a 0 to 5 volt signal input range. As I mentioned, we integrated the GPS system, and the language itself is similar to C++. And I'd had C++ years ago in undergrad, and it did not come back to me. It was it was a bit of a fight, a little bit. So an impact signal, we actually put a 1 meg ohm resistor between the positive and negative to get our zero balance there on our impact. And so our hardware cost on this is only about $40. So the boards itself, the Arduino was 35, and I think the top shield, that's like $20. We're a little over that range, but in terms of that type of system, it's fairly cheap. So now we're just looking at other material costs, and can we make this thing work? So I actually do a power and a data toggle. So the data switch is connected to one of the digital I/O modules. You just check to see when it goes to high, and it starts writing data. So you're not, you can power it up, let it collect its GPS information, and go ahead and crank up the data. So as I mentioned, SD card, micro SD card data storage, and that's kind of what it looks like. My wiring job is this was fast and dirty, and I'm not proud of it whatsoever. But we got it to work in a pretty short time to try to take it out to the field this year. Two different prototypes. The 101A here, this shallow pyramid, that is the NASA design that's in the Lane paper. We duplicated the size, and it is the same size as a conventional hail pad. We tried to do a three-sided delta shape and wanted to put piezo sensors on each plate, so maybe you could get at maybe angle of impact or any kind of wind-blown effects, and it just turned out to not necessarily be, it wasn't the most consistent when we started doing some ice ball impacts with it. And the total cost for these were only about $400. So on the three-sided one, we use swinging tripod legs that can be extended, and they simply fold up under the device. So it's only about this big or so. One person can easily handle it. The tripod legs extend for leveling. There's a bubble level on it, so that actually takes up some deployment time when you're trying to get a nice level there. And then the four-sided kind of shallow pyramid, we just use a single large bolt underneath and bolt the plate of the tripod leg to the bottom of the whole unit that's kind of enclosed by some brackets here. So it's very fast. All you're doing is screwing one bolt onto the tripod legs, and you're good to go. This one, the delta shape was designed with camera mounts, so we could actually try to look at some of the impacts using camera systems. That's been kind of hit or miss, and these are by far not even in a very finished form. It's very new. So there's kind of the nitty-gritties of the designs itself. So following the Lane paper, you have a square weld at the apex of the pyramid with the piezo mount. We also notice if you try to use adhesive, you will definitely cause a voltage signal that can bias your information if you actually put a adhesive on the piezo. So we actually use set screws, very, very tiny set screws that are off the ceramic portion of the disc, and they're all uniformly torqued to hold that piezo, so we don't try to bend it and induce a voltage bias there. And the same applies to the delta shape after we decided to go away from a piezo on each face. So there's one of the first deployments of one of the probes, and you definitely can do it in less than 2 minutes. And I'll show a little bit of data. So as a raindrop or hailstone impact the device, you get that nice impact signal, and you can sample fast enough to actually extract some information. Now, you could get simultaneous impacts, and you just kind of sacrifice some of those things, knowing that you wouldn't be able to extract that. The question becomes calibration. So in the lab, I can take a compressed air can, essentially a fancy potato gun, shoot ice stones at this at a known velocity, look at the impact signal, and develop the calibration curve that way, assuming hailstones all fall at their terminal velocity, and go from there and work off that to back out a size bin. Or, as what we actually done, or we measured hail at the location of the probe. So now we have a distribution of sizes that likely the probe may have seen. So the first real case was 2 weeks ago. I guess it's 2 weeks ago, might have been less than that, near Beaumont, Kansas. And here's what it actually looked like. There was one cell that passed over the probe, and then we looked up and got the hook portion of a Supercell. I kind of joked that this was a better lucky than good kind of deployment. where you're targeting that initial cell that essentially kind of gusted out a little bit. And then we lucked up and got another supercell that passed over the probe after that. So we kind of got in that hook echo, there was a lot bigger hail with this individual supercell than what was actually measured at the probe location. But this is kind of what the data you get looks like. So you have a time history. We see some impacts here from that initial cell. The question is, are these large drops or is it very small hail? And I think you can get at that with maybe some of the frequency content of the individual impacts. The one disadvantage of the Arduino is you have to do a lot of this in post-processing. So you just get essentially a voltage output, and if you try to do any computations within the device processing, it slows down its ability to run at the sampling rate you need it to. And then the next scale, we get a large concentration. So these are essentially impacts per minute, and I have no size algorithm or anything built into this. So we're looking at essentially a relative magnitude, or as a percent of full scale of what the thing can handle in terms of a voltage range in our piezo. So the question is this hail here? Is the hot spot, the hot colors, is that related to large drops, or is it actually small hail? And there's what the distribution of sizes look like that the field teams actually measured. And it's a little hard to see, but the peak is somewhere around 18 millimeters or so. So we're still under we're sub-severe, less than an inch. And there's a photograph of actually what the stones look like on the ground adjacent to the probe. And so the idea is to try to expand upon this, make this better, develop the calibration curves to extract some size information. It's just an automated hail pad. And we have actually hail pads ourselves, and the next deployment we'll probably set them out right next to the device and use that as a possible way to do some calibration work with that. So we try to fill in that distribution gap where stones may have melted before they could be collected and then measured. And so there's kind of the to-do list essentially is looking at distinguishing the large raindrops from the smaller hail. Could you do this, as I mentioned, with hail pads or the field measurement, or even the photogrammetrics, so using the camera systems to look at individual impacts on the plates? What we've noticed, the material properties of the devices are different. It's the quality of the welds, making sure your piezo mounts are essentially as uniform as you can make them. Explore fixed platform deployment, maybe on the West Texas Mesonet or Oklahoma Mesonet, something like that. With the new generation of Arduinos, we already tested one, you can get over 1 kilohertz sampling. We've even talked about using laser welds to make sure we have a very uniform weld on our plates and that mount underneath for the piezo. So a little bit of machining done. And the whole goal is really just like StickNet, to be able to have a network that you could deploy out ahead for all these different kind of applications that you could use. So various meteorological aspects, engineering side, once again, we're charged with trying to improve catastrophe models, and this kind of plays into some of that. To finish up, just to acknowledge, that's my better half, the first one, Tanya Brown, who helps with this project. Also, Matt Kumjian, who did a postdoc here at Penn State, has just kind of gotten involved with using some of the actual physical hail measurements. And some of the work, the Instron testing, was all done at State Farm Insurance, their technology research and innovation lab. They did the Instron comparisons. And so with that, thank you. It's been a nice day so far, somewhat intense, and I've done some figure eights around the building and may have gotten lost once or twice, but with that, that's all I have. So thank you for coming.
Sorry. Any questions? I guess we'll still use the mic so the people that are recording it can listen in.
I saw Steve earlier. I think I'm one of the weirder people with a diverse background that is I've come across in a little while. But this was something that kind of pushed me outside of my realm of comfort, and it was neat to explore some of it. Wow. Yeah.
Well, I have some friends study before about the insurance estimation of how sometimes the debris of a hurricane hit the building, and based on the direction, it probably will have different impact. And also, different houses, even just right next to each other, sometimes have totally different impact from a natural storm. I don't know if you ever look at the impact on buildings or.
We actually do, and you're exactly right. Debris modeling is a big deal right now in terms of building envelopes. Hail is somewhat similar. You do see out in the field, if you just qualitatively look at what's on the ground, you definitely see variability. And then you have those cases that just dump a massive amount, when you have to get the snow plows out. So in terms of quantifying or estimating impacts on a typical roof, which is what the catastrophe modelers would want to do, you'd have to take some kind of composite approach and just understand that we're going to go with the mean state. And that's probably, for that application, it's probably a good estimate for their loss, and work off of that, as opposed to trying to capture the variability within those loss simulations.
Thank you.
As my old baseball coach would say, anyone? Anyone?
I noticed that baseball was on. Forgot to mention that on your resume.
Yeah, I'm a baseball nut. I played back in my younger days.
So I guess I'm trying to wrap my head already at the beginning of why the hail would make the ragged edge as opposed to.
We think it has to do with the duration of impact, but we're also, what we've noticed, if you hit a stone on a structural member, the response of the shingle over the top of it is different. You will have a higher damage state. So if you hit a truss, as opposed to just empty plywood with no backing, there's a resistance there, and the impact energetics seem to change, or the damage states become more severe. And that's a little bit about that, and that may have been one of those. But shingles respond sometimes very oddly, and some of that, you saw that high-speed video. When you do a standard test, it begs the question of sample size. Maybe you're getting a couple hard ice stones that fracture a shingle, but the shingle, if you do it 100 times, might not fail. So if you're actually rating a product, it's one impact in 7 different locations. That's it. Instead of sampling, say, 100 panels, but once again, time is money in that sense. They don't want to, nobody wants to pay for somebody to do 100 different samples, but it starts to ask that question: is sample size in terms of product rating causing some kind of misleading information? And I couldn't tell you why stones will create that ring fracture, and that's actually, it's usually about 60 to 70% of the diameter of the stone, whereas of the steel ball, you can even tell it's a very concentrated impact. And that's a metric that people in claims will use to estimate size. They'll go measure that impact mark and then add a little bit and go look and see if there's any reports that correlate with that size. So it's interesting stuff. And I am not a material scientist by any means, and that's why trying to get some of this information in their hands to do some more detailed work is pretty important, especially for the insurers to try to figure out why that happens or how to stop it. I actually truly think one of the bigger issues is the aging and degrading of materials with time. The aging of roofs, is you saw in that one just 2-year-old roof, the amount of those granules that come off. And if you leave that and don't replace it, that asphalt will then just completely degrade due to the UV exposure. And that's a known issue. And which is also why insurers are often very quick to replace your roof following a hail event, because they don't want that to happen. Asphalt degrades means water gets under your shingles. Water gets under your shingles, water gets in your attic, and that's bad. So.
Actually, for that picture, I was trying to see what that was.
Let me go back.
It's
this one? Yeah.
Yeah. Was the aggregate actually abraded, or is that?
This is a fracture here.
Yeah.
So it actually fractures the shingle. And if you actually took a test standard, underneath it, you're supposed to feel under the shingle and see if there's a crack, which means water can permeate through the crack. These all fail, all of them. So now, okay, this looks completely different, but there's still a crack underneath the shingle. So on the test standard, is that okay? Is that good enough? Or is this worse? Could you leave this or that? Or the known issue is the granule loss, where you get that, you can see the black asphalt. Those aren't fractures per se. The fracture might be on the inner edge of that, and you have a whole bunch of granules that got dislodged around it. And now you bring in the UV problem if you don't deal with that quickly, within a couple of months. So it's one reason, if you kind of paid attention to the insurance world and hurricanes, I'm going to throw them under the bus a little bit. They've been very stonewally with people and not wanting to pay claims. But hail's a different animal. They often jump very quickly to cover their claim because replacing a roof is a lot lower cost if you get water in your house and you start having interior damage, and then start to think about contents too. So it's a very different mindset than kind of the hurricane world a little bit.
Sorry. Anyone else?
I think I rambled there.
Ian, a question about the hail pad measurements you're making. Can you say what is the accuracy that you can make them with? You listed some of the error terms, but also what's the goal for the accuracy and why?
A bin size of maybe, inch to, or 1 1/4 inches is what I'm hoping for. So you're going to get some kind of bin of size. That'll never tell you that was 1.5 inches for sure measurement. That's just beyond the goal of what that device could do. Also, in a severe windblown case where you have a very kind of shallow impact angle, the devices they're virtually useless because you get the structure of the impact is completely different, and the signal you get out of the piezo is very different. So the goal, if I can get somewhere in the 1/4 to 1/2 inch bin sizes, I would be very happy with that. And after talking with Matt a little bit, simply knowing that hail was falling was a helpful piece of information for the radar folks. So that was one application, but I would be happy with even bin sizes that were kind of that large. It isn't meant to be a very fine, like a hail pad, you will get a very good, accurate size distribution, but you don't have the time component. So this is meant, it's trying to, you sacrifice one thing to get the other and try to work off of that.
Well, if there are no more questions, I think we'll thank Ian again.